Hello, my name is Zhongnan Xu, and I'm a shared research candidate in the chemical engineering department. And my job works with synthesis and application of catalysts. So my job is to create heterogeneous catalysts, and these are catalysts usually in the solid phase that help with reactions in the fluid phase, or gas or liquid phase. So in general, when reactions start at the products, reactions start at the reactants, and they have to go to the products. But in doing so, you must add enough energy to get it going, which is called the activation energy. And what catalysts do is that they lower this activation energy, so it's easier to happen. An example would be that in order one reaction would be burning paper, and in order to burn paper, you have to start the reaction, and once you start it, it'll just go into when all of it's burned. And so for example, using a lighter to light the paper on fire would be the activation energy, and a catalyst would lower that energy needed. So maybe it would make it easier to light. Maybe your flame would be not as big. So I make those things that make the reactions easier to happen. My chemical reactions are ethylene epoxidation and palmitic acid deoxygenation. In general, ethylene epoxidation is used to convert ethylene into ethylene oxide. And ethylene oxide is used in antifreeze, fibers, solvents, and plastics, and it's actually a pretty big industry in the U.S. Palmitic acid is actually a new application. It's converting algae into hydrocarbons, which is fuel. So this reaction would help kind of lower the energy costs, but giving an alternative energy, which is algae, which is still mostly untapped. In ethylene epoxidation, the catalysts used are silver nanocubes on aluminum. In palmitic acid, the catalyst used is platinum tin on carbon. My job is to make both of these. So the big part of ethylene epoxidation is making nanocubes out of silver. And to do this, you start with ions, which are dissolved from a silver salt, and you keep adding them into the solution, and they grow into little nucleuses. And after you add more, they start growing into cubes. And the hard part of doing this is making sure they are cubes and making sure that they are small. And to change these, make sure this happens, we have to add hydrochloric acid and changing the concentration. Those are the two main variables I change, which is chloride ions in the solution and concentration. And my job is just to see what the best combination of these two things are to get small cubes and, small cubes, that's right. In order to characterize what I have, what you can do is shine a light through the cubes, and they will give you different colors. So these colors are small cubes, and these are large. That's a way to kind of first see on the spot what cubes you have. And so we desire the small ones. So if we see something that has yellow, it's what we want. And another more quantitative way to do this is called UV-Vis, ultraviolet visible spectroscopy. So what we do is we shine visible light and ultraviolet light through the cubes, and we see what's absorbed. And this graph here, it shows that this is the wavelength. So this is visible through ultraviolet. Ultraviolet light on the left, invisible on the right, and we just see where light's absorbed. And just in general, this small peak tells us that we have cubes, and this peak tells us how big these cubes are. If this peak is shifted to the right, we have large, and if this peak is shifted to the left, we have small. And my job is to make sure this is shifted to the left as much as possible. And also, the peak is thin. So if the peak is thin, that means that all our cubes are the same size. If it's thick, it means we have a big mess of different sized cubes. The second reaction I deal with is converting algae into fuel. And though this is more important, it is still new, and there's not as much ways to characterize what I have. So right now, we cannot tell if the stuff has worked, but ideally, we want carbon support, and then we have the brown, platinum, and we'll have tiny amounts of tin on it, and this will help in the reaction. But yeah, right now we're still in the experimental phase. We don't know what the variables are. We don't know what the products are yet. We cannot characterize them. The only way to see if we had made anything different is to run them in test reactions, which convert palmitic acid into hydrocarbons and see if there's a different reactivity by changing the amount of tin. So right now it's still in a development phase. And yeah, so right now it's still going through silver cubes on synthesizing silver nanocubes and platinum tin. Silver is currently, so we know the variables, we know how to characterize it. So right now it's just finding the perfect combination of chloride and concentration. And on platinum tin, we're still trying to figure out ways to characterize it and to see what we have. And that's it. Thank you for listening, and thank you for your time.